in electrodynamics, I mean electricity, magnetism, dynamics, okay? That's how we say electrostatic, magnetostatic, dynamical part, okay? So we will have a sources somewhere here, okay? Let me write this one as source. Source means that maybe, can you see the board? Yeah. Source means that may be what you call point charges, okay? That may be point charges moving, that may be current carrying wire, that may be current carrying wire which is moving again. Is that okay? We call that one a source here. Is that okay? And we find a force on a, we call that one as test charge Q placed at this point. I call that spatial point as x comma y comma z, okay? If you want to say that is x comma y comma z, you have to set your origin somewhere, am I right? Speak out. You have to set your origin somewhere. Again, I have written this one as R, am I right? This one is R. So we are going to place a charge here, okay? The question is, what is the force on this charge which is placed at x comma y comma z, okay, with respect to some origin, okay? This is your choice, I told in the morning, isn't it? This is your choice. There are sources. That source may be group of charges which are stationary, okay? Or that may be some surface charge, volume charge like that. That may be stationary or moving. That may be current carrying wire or whatever, okay? Let me take the most general situation. In the most general situation, force on the charge placed at this point, okay, that will be proportional to amount of charge, okay? So multiplied with E plus V cross B. I hope you know this one, isn't it? Where we call E and B are electric field and magnetic field at this point. We call it as electric field and magnetic field at this point. Is that okay? So now look at here. Forces, again in lab, what you can experience force only, am I right? Suppose if I remove this charge, okay, let me remove this charge, okay? So then again, look at here, in lab, without any test charge, okay, without any test charge, I mean, you have to keep some test charge or you have to move that test charge, okay? Velocity should exist in order to experience magnetic force, okay? So then only you can experience some force, am I right? Then only you can say there exists force, isn't it? Now what I do is I'll do one mental experiment, okay? So I'm going to keep a charge, okay? I'm going to keep a charge and I'm going to move this charge, okay, in space, and I'm going to find the force, okay? Is that okay? Because I have to move the charge in order to find whether there exists a magnetic field or not, isn't it? Magnetic forces will not act on the charge at rest, isn't it? I hope you know that one. Now look at here. I will place a charge, okay? Yeah, then because of these source charges, I will experience some force, obviously, isn't it? Now what I do is I will remove that charge. But I know that at this point, if I place the charge, there exists force. Am I right? Are you getting my point? First I will place the charge. I will just move the charge and all, okay? I will find the force. Is that okay? Then, no, wait a second. So let me conclude my statement. Let me just, again, if you place the charge, obviously, if you place it at rest, you can experience electrical force, am I right? So again, you just move around there, nearby that point, so that you can experience magnetic force also, isn't it? Somehow, again, I know that force exists on that charge, am I right? So even though I remove this charge from that point, okay? So I know that if I place the charge at that point, force would exist on that one, isn't it? Are you getting my point? Now I removed the charge, okay? So nothing in space here.
After removing the charge.
After removing that, there is nothing to calculate, okay? I mean, there is no force to calculate. I mean, again, if I say force on something, am I right? Earlier I have taken force on the charge Q placed at this point. Is that okay? Now what I did, again, I calculated that force, then I removed that charge. But what I know is, the information that I have is, if I place a charge at this point, that charge will experience force. That force is given by this one. Am I right? Are you getting my point?
What kind of force then?
No, wait a second. Again, that force is given like this. That force is what I have given here.
Sir, in 200, I export the charge. And I again put the charge.
No, wait a second. You are not listening. This is, I think, the problem with the English statement. Is that okay? First, I will place the charge here, okay? And I will move the charge around here and I will calculate the force practically, okay, in lab.
That's fine.
So then I will remove the charge, okay? What is there? There is nothing, isn't it?
Remove means where?
I will remove and throw it to infinity.
Okay.
But what is the information I have? If I place the charge at this point, it would experience a force, isn't it? That's the information I have, because earlier I did that experiment.
Okay.
Isn't it? I know that.
This is classical mechanics. Okay.
Yeah, again, you are thinking about quantum mechanics. Sorry. Now look at here. So even when I throw the charge, okay, so I know that if I place the charge there, it would experience some force that is given by this one, isn't it? So now, even in the absence of that, what you call, charge at this point, we will think there exists a field, electric field and magnetic field at this point, because of these sources. Is that okay? And one more assumption we do, if you place a charge at this point, okay, Q, then this electric field and magnetic field will not change. That means these sources will not be affected by the presence of this charge, okay? Again, these you maintain somehow, okay? When you place this charge, these are not disturbing, and whatever the electric field you have assumed earlier, the same electric field exists.
Okay.
Because everything interact with each other, isn't it? You have to carefully define these things. Is that okay? Are you getting my point? After placing this one, these are not disturbed. That's it. After placing this charge, these are not disturbed. Somehow you are maintaining these sources. Is that okay? Now look at here. So even when there exists no source, no test charge, okay? Even there exists no charge at this spatial point, we are going to imagine there exists a field due to these sources, okay? So we call, again, that field may be either electric field or magnetic field or both. Sometimes both will exist. Is that okay? And if you place a charge over there, force you can obtain from these two information, I mean electric field and magnetic field, okay? If you place a charge at that point, you can find the force on that charge using this electric field and magnetic field. Is that okay? So in one extent, these electric field and magnetic fields are a kind of intermediate step to calculate force. What you do, you just throw off that test charge. You are going to assume there exists electric field and magnetic field, okay, at this point. You are going to assume like this. So then you take charge at that point and you find the force, isn't it? That means first you find electric field and magnetic field due to these source charges at this point, okay, with respect to time also, again. So again, that may be depending on time also sometimes. Is that okay? Electric field and magnetic, in the most general, okay, in the most general situation. So then, again, what you do is first you find electric field and magnetic field at this point due to these sources, okay. So then using that electric field and magnetic field at x comma y comma z, shall I write like this? That's the most comfortable way. Let me write electric field at x comma y comma z. It may be time dependent, and magnetic field at x comma y comma z. It may be time dependent, okay. First we shall find electric field and magnetic field at this point of interest, okay. Let me call this point as P. Okay, so first we calculate these two. Somehow, first we formulate the rule so that we can find this electric field and magnetic field due to these sources. Is that okay? So then we place the charge over there and we find the force on the charge using these two quantities. So in one sense, in the mathematical way, okay, this electric field and magnetic field plays an intermediate role to find the force. You don't directly find the force. You first remove the charge and you find electric field and magnetic field, a kind of fields, vector fields at that point, okay? And then you just, place a charge there and you find the force. Okay. If you see pure mathematically, this electric field and magnetic fields are a kind of intermediate step to calculate force. One step before you first find these two, and then you go for force. That's one idea. And other one is, even though in the absence of charge, okay, if we know that charge would experience a force if we place there, even though in the absence of charge, we are going to picturize a kind of vector field in the space actually. So we call this one as vector field actually, electric field and magnetic field. We call that one as vector field. So can you write a couple of sentences? If we know forces are acting on the charge, if we know the forces are acting on the charge placed at some spatial point, acting on the charge placed at some spatial point, okay, if we know the forces are acting on the charge placed at some spatial point, then even when that charge is absent, we imagine there exists something at that point. We imagine there exists something at that point. That something is electric field or magnetic field, or both. We imagine there exists something at that point that is electric field or magnetic field or both. E vector, B vector or both. So that's why even in the absence of this any charges here, okay, if there is no charge you can't calculate force, okay, even in the absence of any charge, okay, again if you have some sources, okay, which generate electric field and magnetic field as you know, so what we do is each and every point in space is associated with the vectors. Each and every point in space is associated with the vectors. Okay, again we call it as electric field, which is a function of x comma y comma z comma t vector. Okay, it may be function of time also, isn't it, in the most general case. Okay, each and every point in space is associated with two possible vector. One is electric field, other one is magnetic field. Okay, it may be function of x comma y comma z as well as time. We call them as vector field actually. Each and every point, these x, y, z are variable, time is also variable. Is that okay? Now what do you mean by this vector field? So we shall see closely mathematical. Okay, look at here, this electric field as a function of x comma y comma z comma t means usually with respect to some origin, with respect to some coordinate system, we are going to split this one into x, y, z component. Am I right? What do you mean by this electric field which is a function of x, y, z and t, isn't it? That means its component, x component, is a function of x comma y comma z comma t into x cap. Its y component is a function of x comma y comma z comma t. Its z component is a function of x comma y comma z comma t. Is that okay? So these fields, these vector fields are function of space and time. That means, so that is equivalent to, you have three functions. Look at here. Can I say f1, f2, f3? There are three functions here, which are function of x comma y comma t. If you say a field which is a function of space and time, so that is equivalent to each of its component. These are component. Look at here. This is x component. This x stands for component. Okay, this x stands for variable. It's a function of, like that. This y stands for component, y component. Okay, So this x, y, z, these are variable, okay? Ey is a function of x, y, z, comma t. Is that okay? So that means if you define a vector field like this, that means so that vector field, okay, it is a collection of three functions actually. Three spatially varying function, and time dependency may also be there. Is that okay? So it's a collection of three functions. So let me write f1, f2, f3. f1 is this one, f2 is this one, f3 is this one. The same holds for magnetic field. We shall see that one mathematically like this. Now these are vectors, am I right? How do you visualize these vectors, isn't it? How do you visualize this vector field? Again, how do you define a field in first place? What do you mean by field? These are vector field, am I right? Scalar field can also be there, isn't it? How do you define a field? Yeah, so take a statement, okay? Take a statement. Field is any physical quantity. Field is any physical quantity. Field is any physical quantity which takes a different value at different point in space. And it may have possible time dependence. Continue. It may have time dependence also. Is that okay? It may have time dependence also. So in case of fields, you can categorize into two: scalar field and vector field. Is that okay? So for example, again, the best example for the scalar field is, okay, so you have a what you call candle here. Is that okay? You have a candle here. So place that the what you call, suppose again this candle is placed at the what you call, so origin. Let me think like that. Is that okay? And you are finding temperature at this point. Suppose candle what do you call, this flame is decreasing or something, okay, changing. So in that case, look at here. Again, your temperature can be function of x comma y comma z. Am I right? If you move this point, you will have different temperature at different point in space, isn't it? And some, again, suppose if candle flame is what you call that it is decreasing. Suppose that this flame side, this may have possible time dependence, isn't it? But it is a scalar, isn't it? Temperature is a scalar, isn't it? So that comes under the scalar field. The best example is temperature as a function of x comma y comma z comma t, isn't it? Scalar field. We call it a scalar field. Why? It will add like a scalar. Okay, if I place one more candle here, okay, if I take temperature due to first candle as T1, temperature due to second candle as T2, again, the net temperature I can just add, isn't it? They add like a scalar. That's why we call it a scalar field, isn't it? The best the best example is for this vector field is, suppose if you have a what you call water which is flowing in the pipe like this. Is that okay? Water which is flowing in the pipe like this. Is that okay? So velocity field, okay, velocity of this water molecule, you can define like this, okay? That velocity of the water molecule, that may be what you call function of x comma, that is a vector, okay, x comma y comma z comma t, isn't it? We can call it as a vector field, isn't it? Velocity of a water molecule or something. Again, so it may be different at different point, isn't it? And it may vary with time also, isn't it? Suppose you are pushing it here, okay? In the most general case, that's a vector field. And our electric field and magnetic field, these are also fields which are vector field, okay? So which are due to these sources actually, sources which are somewhere. So, but they are function of x comma y comma z comma t. They are vectors, okay? They are vectors. They add like a vector. That's why they are vector. Okay, we shall see that. So now, how do you picturize this vector field? Scalar field, you don't draw anything, okay? In case of vector field, so there are different ways of what you call mathematical representation. You can represent by, again, suppose I told each and every point in space is associated with the vectors, am I right? Electric field and magnetic field. You can write what you call arrow at each and every point in the space, and length of the arrow you can account for what you call strength of the vector field at that point. Okay, that is one way. Other way is what you call drawing vector field like this. Okay, drawing vector field like this. Drawing vector field like this. Okay, so that, I mean, drawing vector field continuously, where this curve, whatever I have drawn, those are what you call tangent to these vectors. Okay, at each and every point in space. And again, this what you call density of this field line. Now look at here. Here you have more density. Here you have less density. Am I right? The density of field line will talk about the strength of the vector field. So in this kind of representation, sometimes again you can account for length of this whatever the vector you have drawn in space. That will talk about strength of the vector field. If length is large, strength is large. If length is small, strength is small. Okay. So there is another representation. Actually, we go for this one later. We shall see. Okay, representation of a vector field, where density of the field line. Can I say density or number of field line per unit area? If you place a what you call plane over there, isn't it? Per unit area passing perpendicular to some plane that you place there. Is that okay? You can think like that. Okay, the density of field line. So that will talk about strength of the field. That is another way of representing that one mathematically. Is that okay? We shall see all of this one after we define the field in terms of x, y, z. Flux is a different concept. Flux is what you call measure of number of field lines. Wait a second, I'll come to that point. Okay, wait for a while. I'll come to that point. But what I'm saying is, whenever you draw, again, these vectors have both direction and magnitude, isn't it? Yeah, you have shown, again, here in this representation, you have shown direction as well as magnitude. Am I right? At this point, vector is like this. 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 Am I right? At each and every point, you have shown direction as well as magnitude. Magnitude by the length of the vector. Suppose at this point, you have very high vector field. Is that okay? But in this representation, look at here, you have shown a continuous line. Am I right? At some position, how do you talk about strength of the vector field? That is given by, in this representation, that is given by density of the field line actually. How close those field lines are. We call this one field line. The word came, look at here. There are two representations. Usually we choose this one. We shall see that one. Okay? We don't choose this one. Representation of a vector field. That's what I'm talking about here. Okay? Wait a second. First we shall work out something, mathematics. Then we shall see how to draw that one. The whole electrodynamics is working on this whole concept. Look at here. You have some charges here. Let me write Q1, Q2, Q3, Q4. Okay, you have some charges here, which may be at rest or which may be moving. We call them as source charges. Okay. Okay, it may be at rest or moving. Okay, which may be at rest or moving. So there are source charges which may be at rest or moving. Okay, so we know their location. Okay, with respect to some origin. Let me take some origin here. With respect to some origin, we know their location. We know how they are moving. We know the velocity of them and all. Okay, we know the acceleration of them if they are accelerating. Okay, we have that information. We call that one as source charges. Okay, so again, this is noun. These are present. Okay, what is the force on the test charge placed at this point somewhere? What is the force on the test charge placed at this point? Okay, can I call this as source charges? Source charges. Okay, which may be at rest or moving in the most general case. So this is the test charge. That test charge may be again at rest or it may be moving. Is that okay? So now look at here. Now look at here. Let me take this test charge somewhere here. Is that okay? Let me take some test charge somewhere here. Now let me take origin somewhere here. Is that okay? Now let me call this one as location of test charge from the origin. Is that okay? Now what is the information I have mathematically? I have this one, I call this one as R1 prime, isn't it? In the morning we have discussed this one R2 prime, this one R3 prime, isn't it? What I know is, I know the location of these charges, source charges. I know I have the information of R1 prime, R2 prime, R3 prime, okay? I know how they are moving. I know the velocity of them, okay? This is the information that I have, okay? I call them as source charges. What is the force on the test charge placed at this point? So whose what you call, so position is R vector. Is that okay? So that is the question. Is that okay? Our ultimate aim is to find the force on the test charge. So again, having the information about some source charges which are at rest or moving. Is that okay? So that is the whole story of electrodynamics. Look at here. So obviously, again, these may be moving also. Okay, these what you call, these charges may be what you call, so moving also. So what do we do here is, look at here, to calculate the net force on this Q. Okay, due to all of these force charges. So it's very difficult, am I right? There are many force charges which are moving and all, isn't it? To calculate net force, it will be very difficult. But nature is quite kind for us. It will allow one, what you call, it will allow us to calculate this force very easily. So that is because of superposition principle. Can you write down superposition principle? Not quantum superposition principle, don't go there. Superposition principle. So can you write down? Interaction between any two charges is completely unaffected by the presence of other charges. Is completely unaffected by the presence of other charges. Let me take, suppose, so Q1 is interacting with this Q, okay? So that is leading to force F1. Let me say F1, okay? F1 is the force due to Q1, okay? Okay? So similarly, let me what you call, define some interaction between Q2 with capital Q. Let me define F2, that is force on this capital Q, okay, due to Q2 and so on. Is that okay? Now, according to this principle of superposition, okay, so what we can do is we can calculate, okay, even though there are many charges here, okay, even though there are many charges here, we can calculate these forces individually. We can calculate forces due to individual source charges and we can vectorially add them. Net force on Q, that will be equal to F1, force due to Q1 only. While calculating this one, you are going to assume there exist no other charges. While calculating this one, except Q2, you are going to assume there are no other charges. Okay? So this superposition principle will allow us to find net force on Q in terms of individual forces. We can find net force on Q is equal to F1 vector plus F2 vector plus F3 vector, force due to third charge, and so on. Is that okay? This is allowed by the nature and it will make the problem quite simple. Is that okay? If superposition principle doesn't exist, okay, it would be very difficult to, what you call, find this net force due to many charges, many source charges. Is that okay? And one more thing, look at here, we didn't take superposition principle to simplify the math, okay? It is a natural thing. Are you getting my point? Okay, actually if you see very closely, you will understand later that superposition principle exists because these forces, okay, these forces definitely proportional to this one, am I right? You are going to write like this again in the most general case, Q into E plus something, am I right? This force definitely proportional to this one, am I right? This F1, these individual forces, okay, those individual forces depends only on these, what you call, these are proportional to first power of these charges actually. Suppose if you take F1, okay, that is proportional to first power of this charge. F2, this is proportional to first power means not square or something, okay, Q2 actually. This allowed us to have that superposition principle actually, okay. If that is proportional to charge square, that superposition principle would not exist actually, okay. So you will see that one when you work out some more. You will feel that one later. Is that okay? So what is the superposition principle? Interaction between any two charges is completely unaffected, okay, by the presence of other charges. This will allow us to find force on this charge due to these individual charges, okay, and vectorially add them. Is that okay? So this whole thing is backed by the superposition principle. Is that okay? This whole thing is backed by superposition principle. Is that okay? Now again, why I told that again that idea is because look at here. If suppose this force is proportional to charge square, okay, then force due to two charges, okay, then what will happen is that will proportional to Q1 plus Q2 the whole square. Am I right? Again, this small q is source charge, okay. If that force is proportional to this source charge square, okay, then force due to two charges, that's equal to sum of the charges square, am I right? So then what will happen here? You will get q1 square plus q2 square plus 2q1 q2. You will get some cross term. You can't write this force as some f1 plus f2. Are you getting my point? You can't write like this. Are you getting my point? If these forces on that charge, if those are proportional to square of the charge on the source charge, okay, then the superposition principle would not exist actually. So these forces, they are proportional to first power of these charges actually. Because of that, the superposition principle exists. Read out first page of electrostatic chapter, okay, of Griffiths carefully. You will understand this one. Is that okay? If suppose these forces proportional to square of the charges, source charges, okay, then look at here. What will happen? Force due to two charges. How do you write? This is force due to 1, okay. Force due to 1 and 2. How do you write? Q1 plus Q2 the whole square. You can't decompose that one into F1 plus F2. It would be too difficult for us to calculate the force actually. So that's why that superposition principle, okay, mathematically it is because of that one. Force is proportional to first power of charge, source charge. Is that okay? Because of even if you say force is due to electric field or magnetic field, okay, plus V cross B. In case of magnetic field also, if you see closely, you will not get square of the charges, okay, you will get first power in charge. We shall see that one. Is that okay? So I'm trying to what you call fuse this physics part as well as mathematics part, okay. Reasoning from physics part, reasoning from mathematics part, okay. And now look at here, this is not again he's going to write in Griffiths, he's going to write very nicely. Superposition principle is not logical necessity, it's not to what you call simplify the math, okay. It is nature, it is experimental fact also. It is experimental fact. Experimental fact means it is nature. Is that okay? Yeah, speak out now.
Sir, if a force depends on quadratic terms, then the interaction will be taken care of then?
No, then also, to find net force due to many charges, it would be so difficult, isn't it? Speak out. I think then electrodynamic syllabus would not be there in our syllabus, isn't it? If nature behaved like that. It is so difficult actually. Is that okay? So try to read that book carefully, you will understand all of this point. Is that okay? Now look here. That's why net charge on this test charge I can find by calculating what you call a force on this one due to Q1, force on this one due to Q2 and all, isn't it? So that's why if I formulate the rule for one of these forces, okay, then that is almost done, am I right? I can just find I can use the rule for all other charges and I can find the net forces, am I right? I need to formulate rule or law so that I can find one of these forces, okay, forces due to one charge. If I calculate force on this test charge due to one of the charge, that would be sufficient for me, am I right? Let me take one source charge here, so test charge Q here, is that okay? So if I find force on this one due to one of the charges, if I formulate that force law, okay, law of that force, that would be sufficient, am I right? Then if I have many charges, I can calculate that forces individually, I can vectorially add them, isn't it? So let me call this one as some italic R. We have taken, am I right, from source charge, source point to field point like that, isn't it? Italic R. So source charge, so test charge. Okay, to formulate this force, okay, to formulate this force, let me say some force exists, okay, to formulate this force, okay, what does this force depends on, okay, let me just list out that one. What does this force depends on? This forces depends on many factors, okay. It depends on the separation. First one, it depends on italic R. It depends on the separation between those two charges. Usually it is inversely proportional to square of the separation. I hope you know that one. In case of, even in case of magnetic field, the similar thing will happen actually. Is that okay? One thing. So second one is, it depends on this charge, this Q also, am I right? Depends on this capital Q as well as small q, and that is proportional to first power in this capital Q, first power in this small q. That's what I told. That force, that depends on these charges also, okay? Those are proportional to this capital Q into small q in most of the case. Is that okay? And third one, it depends on velocity and acceleration of this Q. Velocity and acceleration of source charges. And in some cases it depends on velocity of this Q also, am I right? You know that one. Magnetic force, that's equal to Q into V cross B. That depends on velocity of, capital Q, test charge, am I right? That depends on velocity of the test charge, isn't it? You know this one. Velocity of capital Q also sometimes, okay? Now look at here, in the case when the source charges are moving, okay, it is very, very difficult to find the, what you call, force actually, because we need to respect relativity, isn't it? So if this is at rest, we can find the force, that's not a big deal. But if this is moving, if this is accelerating, then it's very difficult to find the force actually. I mean, it's very difficult to find what you call, it's very difficult to work out the ideal theory for that force actually, because what will happen is, if it is moving, again, that news that it is moving, that's a kind of news, am I right? That news travel with the speed of light actually. It takes some time to reach at this point. So force at this, on this charge, so that is on the, what you call, again, that depends on the location of this charge at some time earlier actually. Is that okay? Let me discuss this one at the later part of the electrodynamics, okay? So if it is at rest, it's quite easy, but if it is moving, okay, so it is very difficult to formulate that force actually. We shall see that one later.
What is the force on one basis?
I mean, you have to do some law or something. You have to say this, suppose Coulomb's law, which will give electrostatic force, am I right? Like that. to formulate that force, okay, if this is moving, it's very difficult, because if this is moving, look at here, suppose at T1 it is here, am I right? At T2 here, it is moved from here to here, okay? But this news that it has moved from here to here, that travels only speed of light. That news will not travel to this point instantaneously. Are you getting my point? That news should travel at speed of light. So that's why, again, if you want to find force at this Q, okay, force at this point, force on the charge at this point, okay, you can you can find the force. What do you call? So it is quite difficult, because how to say, you have to consider where was the charge before actually. Is that okay? You can only do that one, okay? I mean, that part is quite difficult. Just take it like this. Let me explain later. Is that okay? Because I need to work out some more. So that's why, I mean, suppose if you are finding force at T2, at time T2, is that okay? If you want to find force at time T2, you can't take that charge is at T2, is that okay? Because again, Q was at this point at time T2, okay? But force at T2 cannot be obtained by placing charge here, because the information that this charge at this point is not traveled instantaneously. It travels with the speed of light, which takes finite time to reach there. Is that okay? So that's why, so force at T2, okay, at this point, okay, that will be due to the charge at some other position, not at T2. The charge at some earlier time, the position of the charge at some earlier time actually. So that's why that is very difficult part. I mean, if it is moving and if it is accelerating, again, it's much more difficult again. Is that okay? Now I'll come to the point of electrostatic, where source charges are rest, okay? Electrostatic. Statics, okay? So that means all source charges are stationary, okay? Test charge may be at rest or it may be moving, okay? Test charge may be moving or at rest. Okay, we shall take, again, there are different possibilities came, am I right, in case of source charges, okay? So among them, if source charges are rest, we call the situation as electrostatics. Is that okay? Again, this chapter is to study that electrostatics. Electrostatics. Okay, can you write in brackets? Source charges are at rest. Source charges are at rest. Superposition principle allows even when source charges are moving, okay? Even in case of magnetic field, superposition principles are allowed, okay? Is that okay? So if source charges are moving, magnetic fields are going to create, isn't it? And magnetic forces, yeah, definitely. Even when source charges are, the superposition principle exists. Whether it is electric force, magnetic force, that okay, you can apply superposition principle. That's a very good question. Okay. Now, in this situation, again, what I have taken what you call. Let me take origin somewhere here. Okay, origin here. Let me take source charge here. Again, as I told, this source point, am I right? Point of this source charges, we have defined it by r prime vector, isn't it? R prime vector. So now you have a test charge here, Q. Okay. So we have taken that one as a field point, am I right? Because even when you remove this test charge, you are going to assume there exists some field, isn't it? That's why we call this one as field point. Okay. Field point. Again, that's the position of test charge. Okay. So that we have written it as r, vector r, am I right? Speak out. And this separation vector between this one, we have written this one as italic R vector. Am I right? That italic R vector was equal to R vector minus R prime vector, isn't it? Is that okay? Now we shall, again, this is at rest now, okay? This is at rest. So then force on this charge, okay? So force on that charge, that is given by Coulomb's law, am I right? We are formulating force law here, okay? Coulomb's law. Coulomb's law, that is given by force on this charge, okay? So that is equal to 1 by 4 pi epsilon naught in case of SI unit, okay? 1 by 4 pi epsilon naught. So Q into capital Q divided by R square, it's an inverse square law, okay? Distance between them the square, okay? Inverse square law into R cap. What is R cap? R cap is unit vector along this direction. Can I take like this? R cap is a unit vector from this point to this point. Is that okay? You can write this R cap as R vector divided by modulus of R vector, isn't it? Sometimes we write like this, okay? Again, this R cap by R square. Sometimes we write R vector divided by R cube also, okay? This R cap by R square, sometimes it is written like this, okay? R cap by R square, okay? Sometimes we multiply and divide by, again, one more italic R. We write this one as R vector divided by R cube, okay? But I feel comfortable with this one so that I can say it is inverse square law, isn't it? That's why I'm writing like this. So this is a Coulomb's law, isn't it? Where epsilon naught is permittivity of the free space, that is given by, can anyone tell me, 8.85 into, so 10 to the power minus 12 Coulomb square per Newton meter square. 10 to the power minus 12, yeah, that's what he mentioned. Is that okay? And R vector, that italic R vector, it is given here. Is that okay? Speak out. This is a force law. Again, we know that one, right? It depends on product of these two. Suppose if these two charges are, again, there are two kind of charges. I hope you know that one, okay? So if both charges are positive, then force is repulsive, am I right? So force on this one, okay? Let me take this. This is italic R cap, am I right? This is italic R cap, isn't it? That's the direction, okay? If both charges are positive or if both charges are negative, then this product will be positive only, right? This is already positive, so that this whole quantity is positive. So the force will be along this direction. We call it as repulsive, isn't it? If both charges are positive or if both charges are negative. If one charge is positive, other charge is negative, then this product is negative, so that the whole quantity is negative. So negative of R cap, that means that force will be towards this one. We call the force is attractive, isn't it? Everything is there, all information is there here, okay? Whether it is attractive or repulsive force, that depends on whether charges are like or unlike. Is that okay? Speak out. This is about Coulomb's law. Now, if you have many charges, okay, many source charges, you calculate force due to individual one using Coulomb charge, and you vectorially add force to find the net force at that point. Is that okay? So that is allowed by superposition principle. That is allowed by that way of calculating forces due to individual charge and vectorially adding them. That is allowed by superposition principle. Is that okay? So that's why, look at here, Coulomb's law with that superposition principle. Coulomb's law with superposition principle constitutes the physical input for electrostatic. That's how he quotes. Coulomb's law with superposition principle, that constitutes physical input, okay? That's only physical input. Rest of the things are only mathematical elaboration. Physics is over here. Coulomb's law plus superposition principle, physical input is over. Rest, whatever we work out, just like Gauss law or whatever we work out, potential formalism, it is to make the things easier. Those are mathematical. Is that okay? It is to make, it will help us to calculate this force easily due to complex situation of source charges. Is that okay? Now let me take many charges. Any question here? Speak out. Any question here? So shall I proceed?
Sir,
Yeah.
sir,
Hmm.
during calculating the force, do we take the sign of the charges also in account?
Everything is there. Look at here. That's what I'm saying. If both charges are negative, okay, then force is repulsive. Repulsive means it is along r cap. Look at here. This is r cap. Am I right? Whether this is positive or negative, that will decide the force, isn't it? Force direction. Am I right? If both charges are negative, the multiplication is positive. Then force is along r cap. R vector is here along r cap. That means it is repulsive. It is repelled from that charge, isn't it? We say like that. If suppose one is positive, other is negative, this multiplication is negative, this whole thing is negative, then it is negative of r cap. In that case, we say this q is attracted towards small q, isn't it? Everything is there in the force law. See that one mathematically. Is that okay? Q1, Q2, Q3 like this, okay? You have Qi here, which is whose position vector is Ri prime vector, okay? Source charges, these are source charges, okay? Now I have a test charge Q here, which is at a position R vector. R vector is a position of vector of this one. Is that okay? So now again this is a separation vector. Can I write this one as Ri vector, italic Ri vector? Is that okay? Now to find net force on this one, I can find force due to Q1, force due to Q2, force due to Q3, force due to Qi. I can vectorially add them, isn't it? That's why net force, we can write it as F1 vector plus F2 vector plus F3 vector plus and so on. Am I right? Can I write like this? So that means F1 is nothing but 1 by 4 phi epsilon naught, okay? Q1, force due to Q1, Q1 capital Q divided according to Coulomb's law, okay? R1 square into R1 cap, can I write like this? Suppose it is Q1, so this is straight line, okay? So this is R1 vector, is that okay? Can I take like this? R1 square into R1 cap. Similarly, 1 by 4 phi epsilon naught, okay? So Q2 into capital Q divided by R2 square into R2 cap. So plus and so on, can I write like this? Is that okay? Now let me write in a summation format, okay? So summation over I 1 by 4 phi epsilon naught, okay? Qi capital Q divided by Ri square Ri cap, isn't it? Where I equal to 1, 2, 3 and so on. Suppose there are n charges, capital N number of charges, you can suppose, so total n number of charges, n point charges. Is that okay? You can write like this. I'll not notify this one, I'll just write summation over I. Is that okay? So you can write net force like this. Each of these individual forces are due to Coulomb's law. While finding each of these forces, you assume there are no other charges. While finding forces between Q1 and this capital Q, you assume other charges are not affecting that force, calculation of that force. That is the principle of superposition. Is that okay? Now what you do here is you are going to take this capital Q outside. Force on this one, okay? Force on this one, capital Q. That's equal to, we are going to take capital Q outside. You are going to write summation over I 1 by 4 phi epsilon naught, okay? Qi divided by Ri square Ri cap. Is that okay? Now this is a vector, remember. This R1 cap, R2 cap, R3 cap with different coefficient, am I right? Which is added, isn't it? This is a vector. We call that one as electric field. Q into electric field. Or you can write electric field as force per unit charge also, isn't it? From this expression. Is that okay? Now look at here, this expression that is independent of capital Q, isn't it? That is independent of test charge. We imagine there exists electric field even in the absence of this test charge due to the source charges, vector field. Is that okay? Now look at here. I hope you can follow this one. Now look at here. So this electric field, okay, that is equal to summation over I 1 by 4 phi epsilon naught, okay. So Qi divided by Ri square Ri cap, isn't it? Now remember this Ri vector, okay, this Ri vector, what is this one? Can I write it as R vector minus Ri prime vector, am I right? This Ri vector, that's equal to R vector minus of this one, isn't it? So this Ri prime are constant because source charges are at rest, am I right? With respect to this origin, this Ri prime are constant, is that okay? This Ri prime is equal to constant, they are constant. But they are not, again, because these are not moving, isn't it? So that's why when you see this one carefully, look at here, this depends on Ri cap or Ri vector, am I right? This whole thing. So since Ri prime is constant, this whole thing depends only on this one. Is that okay? Speak out. Because in this vector, which is written as a what you call subtraction of other two vectors, one of this vector is a constant. Even though you do the summation, each of these individual Ri, because these are not moving, they are spatially located, isn't they are at rest, isn't it? In case of electrostatic, look at here, this Ri prime, these are constant. That's why this whole vector, that is a function of this distance only. Is that okay? Can I rub out these things which are quite distracting? Is that okay? So that electric field, that is a function of what you call distance from the origin. That means if you, again, R means you have written x comma y comma z, am I right? If you change this point, okay, if you change this point, your electric field will change. If you change that point, actually this R will change, this Ri will not change with respect to this origin. That's what I'm saying, am I right? So this italic R vector, that depends on what you call difference of this. Again, if you change the spatial point, that means you are changing this one. That's why this is a function of spatial point, spatial variable x, y, z. Can I say like this with respect to origin? We have written this one as x prime, y prime, z prime. I hope you remember, am I right? This point. This one is x, y, z. This one is R prime vector. This is R vector, okay? That's how we write. Now we imagine, even though in the absence of charges, we imagine there exists electric field here, which is a function of x comma y comma z or function of position vector, okay? And that electric field is a kind of intermediate way to calculate the force. Force on the charge you place there, that's equal to Q times electric field at that point. Is that okay? Force on the charge you place wherever here, that's equal to charge of that test charge multiplied with the electric field at the point where you place the charge. Is that okay? Mathematically, electric field is a kind of intermediate step. First you calculate electric field due to source charges, then you go for calculating force. This is the way. Let me take one simple example, okay? So that you should know how to calculate this electric fields and all, okay? Let me take one simple example. I have two charges here, okay? One is Q, other is also Q. Other is also Q, which is separated by a distance D. Which is separated by a distance D. Is that okay? I need to find the electric field. I need to find electric field at a distance Z above the middle of these two charges. Is that okay? So perpendicularly above the middle of these two charges. This is middle point. I need electric field at this point, which is which is at a distance Z above this one. Is that okay? Is that okay? I need to find net electric field at this point. Now look at here, electric field is a vector, isn't it? Okay. Again, you may find electric field some other way, but it's very better to choose a coordinate system, isn't it? Are you getting point? We shall take this one as origin. Is that okay? We shall take this one as origin. This one as x-axis. That's your choice, okay? That's completely your choice. Let me take this one as z-axis. Why? Why it is not sometimes. Let me take this one as z. You have to find electric field at this point, okay? Electric field at this point. Let me take this one as z-axis, this one as x-axis, okay? That's your choice. Is that okay? Along this one you can put x cap. Along this one you can put z cap. Am I right? Unit vector, isn't it? Now, electric field at this point again should be calculated. Am I right? That electric field can be calculated due to, again, electric field due to this one, electric field due to this one. Am I right? I can apply this one. E, isn't it? Let me take this one as so let me take this one as R1 vector. Let me take this one as R2 vector, isn't it? I can find electric field 1 by 4 pi epsilon naught Q by R1 square R1 cap plus 1 by 4 pi epsilon naught Q2 R2 cap divided by R2 square. Can I write like this? Is that okay? Now let me call this field as E1 vector. Let me call this field as E2 vector. Okay, so that net electric field, we say like this. Okay, this is the electric field due to this charge, first charge. This is the electric field due to second charge. Okay, you can just write down this electric field. Am I right? This E1 is in this direction. E1 vector, isn't it? E2 vector, because it is along R2 cap. Am I right? E2 vector is in this direction. Diagram may not be appropriate, just draw it properly, okay? E1 vector, E2 vector like this, is that okay? Now you need to find the resultant of these two. So what we do is, look at here, what we do is, there are different ways. One thing is you can split this R1 vector, R2 vector in terms of what you call z cap and x cap, then you can add. That's one way, okay, but that's quite difficult. You can go for angle, you can go for resolution of this vector, am I right? You can define this angle theta. If this is angle theta, this is angle theta, am I right? You can define E1 cos theta. Again, look at here, one more thing you need to observe, mod of R1 is equal to mod of R2, am I right? These two distances are same. That's why mod of E1 is equal to mod of E2. Mod of E1 is equal to mod of E2. I hope you can grab that idea, isn't it? So that's why these two vectors are of same magnitude but different direction. They are making an angle theta with a z axis. Okay, let me draw it like this. Z cap. Okay. Now let me resolve them into horizontal and vertical component. Since they have same magnitude, this horizontal component vanishes. Am I right? Can you imagine that one? Vertical components adds up. I hope you can deal with this kind of thing, vector, resolution of a vector and all. Okay, let me proceed. So that's why, so since horizontal component vanishes, only vertical component adds up. So your resultant vector magnitude will be, look at here. So can I write E1 cos theta? Mod E1 cos theta. So again, vertical component of this one, E2 cos theta. Am I right? They are going to add up actually. And mod E1 is equal to mod E2, isn't it? That's equal to 1 by 4 pi epsilon naught, a q by, so this italic R1 square or italic R2 square, whatever you write, am I right? R1 square, isn't it? So that's why the net electric field, so that's equal to, look at here, 2 times electric field due to 1 into cos of theta, am I right? 2 times E1 cos theta, simply let me write like this, E1 cos theta, because these vertical components are adding up, isn't it? 2 E1 cos theta, where E1 you can write as 1 by 4 pi epsilon naught, okay, 2 times q by R1 square. Can you write this R1 square? I mean that this distance square, you can just use your Pythagoras theorem, am I right? This is d by 2, isn't it? What is R1 square? D by 2 square plus z square. This square plus this square, that's equal to square of this one, am I right? D by 2 square plus z square, that's equal to R1 square. Can I write like this? R1 square is equal to R2 square, that's equal to, this also d by 2, isn't it? From origin. So d by 2 square plus z square, isn't it? You can write like this. Check this out. Into cosine of angle, okay? Into cosine of angle. Again, I think I have written E1 here. Okay? Cos theta. How do you define cos theta from this one? Because look at here. D is given, Z is given. You have to write your whole answer in terms of the given quantity. Theta is what we defined, okay? Theta is what we defined here to solve the problem, okay? That's why, what is cos theta? How do you write cos theta? Speak out. Cos theta is equal to adjacent side divided by hypotenuse. Am I right? R1. So that's equal to Z by, what is R1? Again, you can write root of d by 2 square plus z square. Am I right? So that's why cos theta is equal to, so z divided by d by 2 square plus z square under root. Not over, okay? You are writing a vector. What is the resultant vector? Since horizontal components are getting cancelled, vertical components are getting added, the resultant is around z cap, am I right? You have to write like this, z cap. Okay? So that, let me write it here, the resultant electric field will be like this, resultant electric field at that point. Okay? I have elaborated, okay? Next time I will not elaborate, okay? 2 into 1 by 4 pi epsilon naught, okay? So q z divided by d by 2 square plus z square whole power 3 by 2. One is raised to 1 by 2, one is power 1 whole power 3 by 2. Along z cap. Along z cap. I'll not elaborate this much next time, okay? You should do it yourself.